The attractive intermolecular forces are often called van der Waals forces in the honor of Dutch physicist Johannes van der Waals. Van der Waals forces can be classified into dispersion or London forces, dipole-dipole forces, and dipole-induced dipole forces. Let's study each of them in detail, starting with the dispersion forces. The existence of dispersion forces was first suggested by Fritz London, and hence these forces are also known as London forces. We know that atoms and non-polar molecules have no dipole moment because their electron cloud is symmetrically distributed. However, due to the constant motion of the electrons, an atom or molecule can develop an instantaneous or transient dipole when its electron cloud is distributed asymmetrically about its nucleus. Let's understand this through an example. Suppose we have two atoms labeled as A and B in close vicinity. For a moment, let's assume that the electron cloud distribution in atom A becomes unsymmetrical. That is, the electron cloud is more on one side than the other. Due to the unsymmetrical distribution of the electron cloud, an instantaneous dipole is developed on the atom A. This instantaneous or transient dipole distorts the electron cloud on the other atom. That is, atom B, which is close to it. As a result of this, a dipole is induced in the atom B. The temporary dipoles of atom A and B attract each other. This force of attraction between the two temporary dipoles is known as dispersion force or London force. This force is important only at a short distance, which is limited to 500 picometers and is inversely proportional to the sixth power of the distance between the two molecules. Another type of intermolecular force is dipole-dipole forces. The dipole-dipole forces are attractive forces that act between the polar molecules with permanent dipole. The ends of the dipoles in a polar molecule possesses partial charges which are represented by the Greek letter delta. For example, in hydrogen chloride, due to the greater electronegativity of chlorine, it attracts the electron cloud more towards itself, and thus its end has a partial negative charge and the hydrogen end has a partial positive charge. The attraction between the positive end of one polar molecule and the negative end of the other polar molecule forms the dipole-dipole forces. The more polar the molecule, the greater is the strength of its dipole-dipole interaction. Due to this, the boiling point of polar covalent compounds is relatively higher than that of non-polar covalent compounds. Dipole-dipole forces are stronger compared to the other London forces. But due to the involvement of only partial charges, they are weaker than the ion-ion interactions. The dipole-dipole interaction energy between the polar molecules is inversely proportional to the sixth power of the distance between the two polar molecules. Polar molecules can interact both by dipole-dipole forces and also by London forces of attraction. The third type of forces are dipole-induced dipole forces. These attractive forces operate when a polar molecule with permanent dipole induces a dipole in a non-polar atom or molecule by deforming its electron cloud. Consider the nonpolar chlorine molecule brought in the vicinity of a polar molecule, such as water. The permanent dipole of water molecule polarizes the electron cloud of chlorine and induces dipole on the electrically neutral chlorine molecule. Thus, dipole-induced dipole interactions come into existence between water and chlorine molecules. The induced dipole moment depends upon the dipole moment present in the permanent dipole and the polarizability of the nonpolar molecule. Larger the size of the nonpolar molecule, higher is the polarizability, and hence greater is the strength of the attractive interactions. In this case also, interaction energy is inversely proportional to the sixth part of the distance between the two interacting particles. A special case of dipole-dipole interaction called hydrogen bond exists in the molecules with highly polar NH, OH or HF bonds. This intermolecular force is stronger than the van der Waals forces of attraction, having interaction energy of the order of 10 to 100 kilojoules per mole. Therefore, hydrogen bond is a powerful force in determining the structure and properties of many compounds such as proteins and nucleic acids. Have you ever wondered why it is very difficult to compress the solids and liquids? Intermolecular forces can also be repulsive in nature. When two molecules are brought closer, the repulsions between the electron clouds and between the two nuclei of the molecules come into play. The magnitude of repulsion increases rapidly with the decrease in the distance between the molecules. In solids and liquids, the molecules are already close to each other, and hence, when we try to compress them, the repulsive interactions would further increase. Hence, they resist compression. The physical state of a substance not only depends on the strength of intermolecular forces that exist between its atoms or molecules, but also on the thermal energy of atoms or molecules. The energy of a body arising from the translational, rotational, or vibrational motion of its atoms or molecules is called the thermal energy. It is the measure of the average kinetic energy of the constituents of the matter and is directly proportional to temperature of the substance. The intermolecular forces of attraction between the molecules try to bring the molecules closer. On the other hand, the thermal energy possessed by the molecules, which results in the movement of molecules, tries to keep them apart. The balance between the intermolecular forces and the thermal energy of the molecules is responsible for the physical state of matter. In gases, the intermolecular forces of attraction are the weakest, while thermal energy is the highest. While the compression brings the molecules to close vicinity, the lowering of the temperature brings about the liquefaction of the gases by decreasing the thermal energy of the molecules. Of the 117 elements known so far, only 11 are in the gaseous state at room temperature and pressure. The gaseous state is the simplest form of matter. This is why all gases show almost identical physical behavior regardless of their chemical nature. They are characterized by the following properties. Gases have no definite shape and volume, and hence assume the volume and shape of the container. Gases are highly compressible, which means that when the pressure increases, the volume of the gas decreases. Gases exert equal pressure in all directions. Gases intermix equally and completely in all proportions without any mechanical aid. Gases have lower density than solids and liquids. The behavior of gases is governed by gas laws, which define the relationship between measurable properties such as volume, V, pressure P, temperature T, and the number of moles N. These properties are interdependent and describe the state of the gas. The four main gas laws are Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. Boyle's law expresses the relationship between volume and pressure. Charles' law expresses the relationship between volume and temperature. Gay-Lussac's law expresses the relationship between pressure and temperature. And Avogadro's law expresses the relationship between volume and number of molecules of a gas. Let us discuss each of these laws in detail. In 1662, Anglo-Irish scientist Robert Boyle, after conducting various experiments, concluded that at constant temperature, the pressure of fixed amount of gas is inversely proportional with its volume. This is known as Boyle's law. Mathematically, Boyle's law can be written as P inversely proportional to V at constant temperature T and number of moles of the gas N. Or P is equal to K by V, where K is a proportionality constant, whose value depends on the temperature and number of moles of the gas. On rearranging the equation, we get PV is equal to K. Or, in other words, at constant temperature, product of pressure and volume of fixed amount of gas is constant. For example, if N moles of a gas A occupying volume V1 at pressure P1 expands to volume V2 and pressure P2 at constant temperature, then P1V1 is equal to P2V2, which is constant. Now consider N moles of gas B at pressure P1 and volume V1. Let us now slowly increase the pressure, keeping the temperature constant at T1. We observe that volume of gas decreases as the pressure increases. If we plot this variation of pressure versus volume on XY graph, we get the given curve. Let us now change the temperature of the gas to T2 and repeat the same process by keeping the temperature constant at T2. In this case, if we plot the variation of pressure versus volume, we get a different curve. From this, we can conclude that each pressure versus volume curve corresponds to a different constant temperature for a given amount of gas. These curves are known as isotherms. Similarly, we can plot variation of pressure against 1 by volume. We get straight line for each constant temperature. These straight lines pass through the origin. The next law is Charles' law that describes the relationship between volume of a gas and its temperature. Jacques Charles and Gay-Lussac studied the relationship between volume and temperature of gases independently. They concluded that for a fixed mass of gas at constant pressure, the volume of gas increases with increase in temperature and decreases on cooling. They found that when pressure remains constant, a fixed mass of any gas expands or contracts respectively by 1/273 of its volume at 0 degrees Celsius for every rise or fall in temperature by 1 degree Celsius. Let's understand this through mathematical expression. Let V0 be the volume of a fixed mass of a gas at 0 degrees Celsius, and let V be its volume at temperature T degrees Celsius at same pressure. Then, volume V at temperature T is equal to V0 plus V0 divided by 273 into T. Or, V is equal to V0 into 1 plus T divided by 273. Or, V is equal to V0 into 273 plus T whole divided by 273. Let this be equation 1. We know that T plus 273 is nothing but absolute temperature in Kelvin scale. Writing T plus 273 as T, we get V is equal to V0 into T divided by 273. But for a given mass of a gas, V0 by 273 is equal to constant. Therefore, V is equal to kT, where K is a constant. Remember, temperature T is in Kelvin scale. This is a mathematical expression for Charles' law, which states that the volume of a fixed mass of a gas is directly proportional to its absolute temperature if the pressure is kept constant. If a given gas occupies volume V1 at T1 temperature and volume V2 at T2 temperature, then by Charles' law, V1 by T1 is equal to K constant, which is in turn equal to V2 by T2. Therefore, the equation can be written as V1 divided by T1 is equal to V2 divided by T2 is equal to K. This is called the Charles' law equation. For a given amount of gas, if we plot the variation of volume versus temperature at different pressures, we get different straight lines corresponding to each pressure. These lines are called isobars. You can observe all the straight lines on extending to zero volume. Intercept the temperature axis at minus 273.15 degrees Celsius. From the graph, if we substitute the value of temperature as minus 273 degrees Celsius in equation 1, then volume at minus 273 degrees Celsius becomes 0. Thus, we can conclude that the volume of a gas would be reduced to 0 at minus 273 degrees Celsius. The temperature minus 273 degrees Celsius
is called absolute zero. This is the lowest temperature that can ever be reached. At this temperature, the molecular motion of gases will stop and will cease to exist. The next law is Gay-Lussac's law. According to Gay-Lussac's law, at constant volume, pressure of a fixed amount of gas varies directly with the temperature. In other words, at constant volume, temperature of a gas increases with increase in pressure and decreases with decrease in pressure. Mathematically, Gay-Lussac's law can be written as P is directly proportional to T, or P is equal to kT, where K is the proportionality constant. The numerical value of the constant K depends upon the amount of the gas taken and the volume. This law can also be derived by combining Boyle's law and Charles' law. If we plot pressure versus temperature for a given volume of a gas, we get straight lines corresponding to each volume. These lines are called isochores. The fourth gas law is Avogadro's law. In 1811, Italian chemist Amedeo Avogadro stated that at same temperature and pressure, equal volumes of gases contain same number of molecules, irrespective of their chemical and physical properties. For example, consider 1 liter of hydrogen gas and 1 liter of oxygen gas. Then, according to Avogadro's law, at same temperature and pressure, both 1 liter of hydrogen and oxygen contain equal number of molecules. Mathematically, Avogadro's law can be written as V is directly proportional to N, where V is the volume of the gas and N is the amount of gas or number of moles of the gas. Replacing the proportionality sign by proportionality constant K, we get V is equal to Nk.
We know that volume, the number of moles, pressure, and temperature are the 4 interrelated properties that describe the behavior of gases. The relationship between these properties is described by 3 laws. They are Boyle's law, Charles' law, and Avogadro's law. Boyle's law describes the relationship between pressure and volume. It states that volume is inversely proportional to pressure at constant temperature and number of moles. Charles' law describes the relationship between temperature and volume. It states that volume is directly proportional to temperature at constant pressure and number of moles. Avogadro's law describes the relationship between volume and number of moles. It states that at constant pressure and temperature, the volume of a gas is directly proportional to the number of moles present in the gas. On combining these 3 laws, we get the ideal gas equation. However, when we introduce a constant of proportionality, R, then the equation can be written as V is equal to R into N into T divided by P. Here, R is known as the universal gas constant. To find the value of R, we need to rearrange the equation and substitute appropriate values of P, V, N and T. For example, under standard conditions of temperature, that is 0 degrees Celsius or 273.15 Kelvin, and pressure, that is 1 atmosphere or 101.3 kilopascal or 10 to the power of 5 Pascal, 1 mole of a gas occupies 22.4 liters or 22.4 cubic decimeter. On substituting the values in the equation, we can get the value of R as 8.314 joules per Kelvin per mole. We have learnt that ideal gas equation is a relation between 4 variables: volume, pressure, temperature, and number of moles of a gas. If we vary temperature, volume and pressure of fixed amount of gas, that is, keeping the number of moles N of the gas constant from T1, V1 and P1 to T2, P2 and V2. Then, using ideal gas equation, we can write P1V1 by T1 is equal to NR and P2V2 by T2 is equal to NR. Combining the two equations, we get P1V1 by T1 is equal to P2V2 by T2. This equation is known as combined gas law and is useful in performing calculating of any of the variable if other 5 variables are known. So far, we have identified the relationship between volume and the other interrelated properties using the ideal gas equation. Next, let's move on to learn about an equation that relates density and molar mass for gas. To understand the density and molar mass of a gaseous substance, we have to rearrange the ideal gas equation to N divided by V is equal to P divided by R into T. On replacing number of moles N with mass of the gas M by M, we get the equation M divided by M into V is equal to P divided by R into T, where M is molecular mass of the gas. We know that M by V is equal to D, where D is the density of the gas. Thus, we can rewrite the equation as D divided by M is equal to P divided by R into T. On rearranging the equation, we get the relationship to calculate the molar mass of gas as M is equal to D into R into T divided by P. The various gas laws that we have learnt establish the relationship among pressure, temperature, and volume occupied by a certain number of moles of a gas. But air is a mixture of various gases. So how do we know the pressure of a particular gas in the mixture? In 1807, John Dalton studied the pressure exerted by a mixture of non-reacting gases enclosed in a vessel. Based on these studies, he formulated the law of partial pressures. According to Dalton's law of partial pressures, the total pressure exerted by a mixture of 2 or more non-reacting gases enclosed in a vessel at a given temperature is equal to the sum of the partial pressures exerted by individual gases, that is, the pressure which these gases would exert if they were enclosed separately in that vessel at the same temperature. To understand this law, Let us consider 3 vessels of the same volume at the same temperature. Let the first vessel be enclosed with A moles of hydrogen exerting a pressure of 0.30 bar, and the second vessel be enclosed with B moles of oxygen at the same temperature exerting a pressure of 0.45 bar. Now, if we put both hydrogen and oxygen gases in the third vessel, the total pressure exerted by hydrogen and oxygen in the third vessel would be partial pressure of hydrogen plus partial pressure of oxygen. That is, the total pressure P total is equal to 0.30 bar plus 0.45 bar, which is equal to 0.75 bar. Generally, Dalton's law of partial pressures can be written mathematically as P total is equal to P1 plus P2 plus P3 plus and so on at constant temperature and volume, where P total is the total pressure exerted by the mixture of gases and P1, P2, P3, etc. are partial pressures of individual gases 1, 2, and 3 respectively. Let us now calculate the partial pressure exerted by each gas from the ideal gas equation. Consider a mixture of 3 gases 1, 2, and 3 enclosed in a container of volume V at temperature T, exerting partial pressures P1, P2, and P3 respectively. Now, by applying the ideal gas equation, the partial pressure of gas 1, that is P1, is equal to N1 RT divided by V. Partial pressure of gas 2, that is P2, is equal to N2 RT divided by V. And partial pressure of gas 3, that is P3, is equal to N3 RT divided by V, where N1, N2, and N3 are the number of moles of the 3 gases. According to Dalton's law of partial pressures, total pressure exerted by the mixture of gases P total is equal to P1 plus P2 plus P3. On substituting the values of P1, P2, and P3, we get P total equals to N1 RT divided by V plus N2 RT divided by V plus N3 RT divided by V. On simplifying, we get P total is equal to N1 plus N2 plus N3 multiplied by RT divided by V. On dividing P1 by P total, we get P1 by P total equal to N1 divided by N1 plus N2 plus N3. Here, RT and V get cancelled. Therefore, P1 by P total is equal to N1 divided by N, where N is equal to N1 plus N2 plus N3, or total number of moles. We know that N1 by N is equal to X1, where X1 is mole fraction of gas 1. For a mixture of gases, the mole fraction can be defined as the ratio of number of moles of an individual gas to the total number of moles of all the gases present in a mixture. On substituting the values, we get P1 divided by P total is equal to X1. This equation can be written as P1 is equal to X1 multiplied by P total. Similarly, for other two gases, we can express partial pressures as P2 equals X2 multiplied by P total and P3 equals X3 multiplied by P total. Thus, a general equation can be expressed as Pi equals Xi multiplied by P total, where Pi and Xi are the partial pressure and mole fraction of ith gas respectively. Thus, if the total pressure of a mixture of gases is known and the mole fraction of the gas is known, then the equation Pi equals Xi multiplied by P total is used to calculate the pressure exerted by an individual gas. Dalton's law of partial pressures is useful in calculating the pressure of the dry gas collected over water by the downward displacement in the laboratory. As we know that a gas collected over water is saturated with water vapor, it is said to be a moist gas. The total pressure exerted by a moist gas is equal to the sum of the partial pressures of the dry gas and water vapor respectively. The pressure exerted by water vapor, which is in equilibrium with water at constant temperature, is called aqueous tension. If the pressure of dry gas and the moist gas are represented as P and P, and the partial pressure due to water vapor commonly called aqueous tension can be expressed as P dash, then by Dalton's law of partial pressures, the total pressure exerted by a moist gas, that is, P is equal to the partial pressure of the dry gas, P, plus partial pressure of the water vapor, P dash. By rewriting the equation, we get the partial pressure of dry gas P is equal to total pressure of moist gas P minus aqueous tension P dash.